On this week, NOAA's Space Weather Prediction Center issued a bulletin that most people never saw, not because it was classified, not because the data was uncertain, but because the warning arrived packaged inside a sentence that forecasters chose with great care. Solar far-side imagery from NASA Solar Orbiter means the forecast could change for May 20th and beyond. That sentence, quiet as it reads, carries the weight of a flare factory rotating directly into Earth's line of fire. What the instruments are now tracking on the hidden face of the sun, unseen by the sensors pointed at us from the comfortable side of this relationship, is an active region whose thermal signature and magnetic complexity suggest an escalating output cycle that has forecasters watching the rotation clock with a precision that borders on anxiety. If this channel has earned your trust by grounding every claim in verified data and explaining it without alarm that outpaces the evidence, then subscribing ensures that what the instruments are measuring reaches you before the headlines are written. The work does not belong to any single broadcast. It belongs to the audience that has decided accuracy matters more than speed. Every figure in this script was drawn from official scientific and governmental sources. NOAA's Space Weather Prediction Center at SWPC, NOAA. GOV, the European Space Agency's Solar Orbiter mission data. NASA's Solar Dynamics Observatory, peer-reviewed research published in astronomy and astrophysics, and the January 2026 report compiled by the United Kingdom's Science and Technology Facilities Council. These sources are not infallible. The human process of reading, interpreting, and translating instrument data into a script introduces its own margin of error. Before any decision is made, whether personal, professional, or logistical, verify independently through the official channels. The data is public. The responsibility to check belongs to all of us, but that is not even the complete picture, because what NOAA's May 18th bulletin described was not simply a region of solar activity rotating toward Earth. It was the most recent data point in a sequence that began building in earnest in January of this year, accelerated through February with 4 X-class flares in 48 hours, and now sits at the convergence point of 3 compounding conditions. Solar cycle 25, running hotter and stronger than the original 2019 prediction panel ever modeled, a thermosphere heating index currently recorded by spaceweather. COM at 16, 56 times 10 to the 10th watts, climbing steadily against a maximum historical value of 49, 4 in October 1957. And a solar far-side active region whose approach to Earth-facing geometry is being tracked by instruments that did not exist the last time a comparable threat materialized. What the viewer has considered a story about a solar storm is actually a story about a civilization that built its entire technological infrastructure during the quietest stretch of solar activity in living memory, and is now watching that quiet end. The sun does not orbit the Earth. The Earth orbits the sun. That distinction, elementary as it sounds, becomes deeply consequential when you understand what it means for solar monitoring. The sun rotates on its own axis approximately once every 28 days. From a fixed observing position on Earth or in Earth orbit, the solar surface visible to our instruments spans roughly half the solar disk at any given moment, the hemisphere facing us. The other hemisphere, the far side, has historically been invisible. Active regions could boil up, intensify, produce enormous eruptive events entirely beyond our field of view, and we would know nothing about them until they rotated into the near side window, giving us perhaps a 14-day warning at best. For most of the space age, this was simply the accepted limitation. You watched what you could see, and you waited for the rest to come around. That changed with the European Space Agency's Solar Orbiter, launched in February 2020, which follows an orbit around the sun that carries it periodically into positions where it can image the solar far side directly. What Solar Orbiter delivered on May 18, 2026 was not simply a photograph, it was a prediction engine. When analysts at the Space Weather Prediction Center examined far-side imagery collected by Solar Orbiter's Extreme Ultraviolet Imager, and cross-referenced it with helioseismic holography data from the Solar Dynamics Observatory, a technique that uses acoustic waves propagating through the solar interior to infer what is happening on the surface, not visible from Earth. They saw what NOAA chose to describe in the careful language of professional forecasters. The forecast could change for May 20th and beyond. Scientists choose their language carefully here, and that careful language is itself the warning. To understand why this matters, it is necessary to establish what the thermosphere climate index actually measures, because it is not a number that makes news, and it is not a number that most viewers would encounter outside a monitoring dashboard. The thermosphere is the layer of Earth's atmosphere beginning at approximately 80 kilometers altitude and extending to roughly 600 kilometers. It is the layer through which satellites orbit. It is the layer where the earliest effects of incoming solar energy are absorbed. When solar activity intensifies, when the sun's output of extreme ultraviolet radiation increases, the thermosphere heats. When the thermosphere heats, it expands. When it expands, It pushes denser atmosphere to higher altitudes, increasing the drag on every satellite in low Earth orbit. On May 18, 2026, the thermosphere climate index stood at 16, 56 times 10 to the 10th watts. The historical minimum during solar minimum conditions, recorded in February 2009, was 2.05. The historical maximum, recorded in October 1957 during one of the strongest solar cycles of the 20th century, was 49. 4. The current reading is not at the historical maximum, but the trajectory matters. We are not at the peak, we are approaching it from below, and the approach is accelerating. Here is where this account becomes genuinely significant. The 10. 7 centimeter radio flux, the standard scientific measure of overall solar output, updated daily and published by spaceweather. COM read 104 solar flux units on May 18, 2026. This is a number that requires translation. 1 solar flux unit equals 10 to the minus 22 watts per square meter per hertz. A reading of 104 solar flux units means the sun's background radio output is running at a level that corresponds, historically, to a solar cycle that has not yet reached its peak, but is already producing the kind of complex magnetic active regions that generate X-class flares. And this is without the far side contribution. The region, NOAA's solar orbiter data, flagged on May 18th, is not yet accounted for in the near side measurements. It is approaching. The system is not inactive, it is accumulating. The people who understand this best are the operators of high voltage transmission infrastructure across North America and Northern Europe. They have understood it in gradually sharpening detail since March 13, 1989, when a geomagnetic storm of sufficient intensity collapsed the entire Quebec power grid in 92 seconds, not minutes, seconds. The Hydro-Quebec transmission system, which served roughly 6 million people in the province of Quebec, Canada, experienced simultaneous protective relay trips across multiple transmission lines at 2:44 in the morning, local time. Within a minute and a half, the cascading failures had left every one of those 6 million people without electricity in the middle of a Canadian winter, in the darkness of a night that had already turned strange with auroras visible as far south as Texas and Cuba and the Canary Islands. 6 million people. The temperature in Montreal that morning was minus 13 degrees Celsius. The blackout lasted 9 hours before partial restoration began, and some areas of Quebec did not have full power back for days. The geomagnetic storm that caused it rated G4 on the NOAA scale, the second highest category. It was not the worst-case scenario. It was not even close. The worst-case scenario on record occurred on September 1, 1859. The event bears the name of British astronomer Richard Carrington, who on that morning was sketching sunspot positions at his private observatory in Redhill, England, when he observed something no astronomer had ever documented before, a sudden intense white light brightening emanating from a cluster of sunspots so brilliant it was visible in direct sunlight to the naked eye, so brief it lasted perhaps 5 minutes before fading entirely. Carrington made careful notes. He reported his observation to the Royal Astronomical Society. He did not know that what he had seen was a solar flare. The concept did not yet exist in the scientific vocabulary, and he could not have known that the coronal mass ejection accompanying it would cross 150 million kilometers in 17.6 hours, roughly 5 times faster than a typical CME. Normal transit time for a coronal mass ejection from the Sun to Earth is 2 to 4 days. The Carrington CME crossed that distance in under 18 hours. When it arrived, it compressed Earth's magnetic field, overwhelmed the magnetospheric shielding, and induced geomagnetically induced currents in every telegraphic wire on the planet. Operators in some stations received electric shocks through their equipment. In others, sparks leapt spontaneously from telegraph keys and connecting apparatus. Some telegraph stations in the United States and Europe caught fire. 2 operators on the line between Boston and Portland, Maine, disconnected their batteries and continued transmitting messages for 2 hours using only the current induced in the wire by the geomagnetic storm itself. The auroral displays were visible near Panama. Gold miners in the Rocky Mountains reportedly woke in the night, convinced. The sun had risen early and began preparing breakfast. It was the middle of the night. The light was the aurora. This is not a hypothesis. This is documented in the geological, historical, and instrumental record. The question is not whether an event of this character can occur. The question is not whether. The question is when. A Lloyd's of London risk assessment model, drawing on established scientific literature, estimated that a comparable event today could cost the United States economy between $0.6 and $2.6 trillion. The range is not due to uncertainty about whether the storm would be damaging. The range reflects uncertainty about one single variable: how quickly extra high voltage transformers could be replaced. These transformers, massive, custom-built units weighing hundreds of tons, manufactured in facilities distributed globally, carrying lead times of 12 to 18 months under normal supply chain conditions, are the single most critical vulnerability in the modern power grid's response to geomagnetically induced currents. They are designed to handle alternating current. A geomagnetic storm produces quasi-direct current flowing through the long transmission lines that act, during such an event, as enormous antennas laid across the Earth's surface. This quasi-DC saturates the transformer cores, creates extreme localized heating, and in severe cases causes irreversible physical damage not to software, not to circuitry that can be reset, but to metal and insulation that must be physically replaced. The low end of the blackout duration estimate, 16 days, assumes rapid deployment of replacement units from pre-positioned stockpiles. The high end, 1 to 2 years, reflects the realistic lead time for manufacturing new units when the existing supply chain has been overwhelmed simultaneously across multiple affected regions. Between 20 and 40 million Americans are estimated to fall within the affected zone in a Carrington scale event. That is a city the size of Greater New York, Greater Los Angeles, Greater Chicago, and Greater Houston combined without power, potentially for periods measured not in days but in seasons. Now consider where those people live and what their mornings look like in the specific geography where the grid is most exposed. The northeastern United States corridor: Boston, Massachusetts; Providence, Rhode Island; Hartford, Connecticut; New York, New York; Philadelphia, Pennsylvania sits at geomagnetic latitudes where the risk from geomagnetically induced currents is highest. The electrical transmission infrastructure of this corridor includes aging transformers, some of which were installed in the 1970s and 1980 seconds and have been operating continuously through every storm cycle since, a resident of Boston's Dorchester neighborhood who wakes each morning at 6 a.m. To a refrigerator that preserves food, a heating system that activates on schedule, a transit network that runs on signals and switches powered by the same grid, a hospital 2 miles north whose intensive care unit runs on uninterruptible power supply systems rated for 72 hours that resident has never once in their daily routine had reason to think about geomagnetically induced currents or extra high voltage transformer saturation or the quiet debt that a civilization owes to the sun's recent behavior. If the data now coming from Solar Orbiter's far-side imagery indicates what NOAA's May 18th bulletin suggested, it might indicate that residents 6 a.m. tomorrow and their 6 a.m. next week are not the same. The question those people would ask if they had access to the instrument data in front of the viewer right now is one the viewer has perhaps already formed. How much warning would we actually have? The answer is specific and it is not comforting. For a near-side active region producing a full halo coronal mass ejection, one where the ejection is directed squarely at Earth, NOAA's Space Weather Prediction Center typically detects the eruption at the time of the associated flare using X-ray sensors on the GOES satellite constellation and issues initial CME arrival predictions. Within minutes, the CME itself takes somewhere between 15 hours and 4 days to reach Earth, depending on its velocity, the January 2026 X1. 9 flare from active region 4341 produced a full halo CME that arrived at 2:20 in the afternoon Eastern Time on January 19th, exactly 25 hours after the eruption at 1809 UTC on January 18th. That event was detected, tracked, and forecast with reasonable accuracy. But the January 2026 event was a near-side event. The active region that produced it was visible. The far-side situation is different. A far-side active region rotating into Earth-facing geometry provides a longer lead time. In one sense, the rotation itself, observable via solar orbiter and helioseismic holography, gives forecasters advance notice that something is approaching, but there is a crucial period between the moment a region crosses the solar limb into near-side geometry and the moment its full magnetic complexity is accessible by the most sensitive near-side instruments. During that window, if an eruption occurs, the available warning time compresses. This is the condition now developing. The solar far-side imagery from Solar Orbiter that prompted NOAA's May 18th bulletin describes activity in a region that is approaching, rotating toward us, and whose magnetic character is becoming readable through the acoustic holography method but is not yet fully resolved. Forecasters have said the forecast could change for May 20th and beyond. The 7 centimeters radio flux reads 104 solar flux units against a background of an already active solar cycle. The thermosphere heating index is climbing. The February 1st and 2, 2026 sequence for X-class flares in less than 48 hours, including one X8, one that NASA's Solar Dynamics Observatory classified as among the most energetic events since the solar cycle's intensification, with the most extreme radiation storm placing it at the top of the GOES records, demonstrated that this cycle has already shown it can produce rapid, consecutive, high-energy events from a single active region. What a connected systems analysis reveals is not simply that the sun is doing something threatening in isolation. It is that the threat sits inside a web of systems that amplify each other's consequences in ways that are documented but rarely presented together. Consider the thermospheric heating that accompanies any significant geomagnetic storm. When enhanced extreme ultraviolet radiation from an active flaring region heats the thermosphere, the density at any given altitude above roughly 400 kilometers increases dramatically. Every satellite in low Earth orbit, including the constellation of navigation satellites, the Earth observing instruments, the commercial communication platforms, and the 6000 plus active Starlink satellites that increasingly underpin military and civilian communications infrastructure, experiences increased drag. The drag is not uniform, it varies with latitude, with solar exposure geometry, with the altitude and mass of each individual satellite. But the effect at the population level is that active solar periods accelerate the natural decay of satellite orbits, require increased fuel consumption for station keeping, and in extreme cases force emergency maneuvers to avoid deorbit or collision. During the intensifying phase of solar cycle 25, the rate of Starlink satellite re-entries due to increased atmospheric drag was documented in peer-reviewed research and quantified against the thermospheric heating measurements. The system is not isolated. The heat that comes from the sun's active regions does not stop at the ionosphere. It reaches down into the operational envelope of every technology system that modern society uses to navigate, communicate, and coordinate. And then there is the second connected system, which is the one that carries the greatest long-term uncertainty. The geomagnetic field itself, the planetary magnetic shield that has protected life on Earth through every solar storm in the 4-6 billion year history of this planet, is not static. The field is generated by convective motion in Earth's liquid outer core, and it varies on timescales from days to millennia. Over the past century and a half of systematic measurement, Earth's magnetic field has been weakening. The rate of weakening has been measured at approximately 5% per century in terms of field dipole moment strength. The South Atlantic anomaly, a region centered roughly over South America and the South Atlantic Ocean where the field dips to only a fraction of its global average intensity, has been expanding and deepening. Satellites passing through this anomaly routinely experience elevated radiation levels and increased rates of electronic upset. A weakened field does not mean a failed shield for the purposes of ordinary solar activity. But it does mean that the threshold at which a geomagnetic storm's induced currents reach damaging levels in surface infrastructure is lower than it was 100 years ago. The shield that protected the telegraph operators of 1859, insofar as protection was even relevant to their much simpler infrastructure, is not the same shield protecting the grid operators of 2026. The field is weaker, the infrastructure is more complex, the dependence runs deeper. There is a third connected system that is less often cited but is supported by documented research and carries what scientists describe as deep instructive value. Solar Cycle 25 was initially predicted by the 2019 International Prediction Panel, convened jointly by NOAA, NASA, and the International Space Environmental Services, to be a relatively modest cycle, maximum sunspot number around 115, peak occurring around July 2025. What actually occurred was significantly different. The cycle intensified ahead of schedule. Activity surpassed the panel's predictions by margins that forced NOAA to issue a revised experimental forecast in October 2023, moving the projected peak forward and upward. By January 2026, NOAA's Solar Cycle 25 progression data showed the cycle running materially above the original envelope. By February 1 and 2, when 4X-class flares erupted in sequence, including an X8, one that ranks among the most powerful individual events of the cycle, the pattern was unambiguous. Solar Cycle 25 had proven stronger than the most widely cited predictions. This is not a criticism of the prediction panel, which worked with the best available methodology and the best available historical data. It is a statement about the fundamental limits of solar cycle prediction as a science. The sun does not conform reliably to its historical precedents. The monitoring is in place and detection is possible, but prediction is not. That sentence is not a failure of science. It is science's honest accounting of what the instruments can and cannot tell us. Consider what that means in practical terms. On May 20, 2026, with a far-side active region approaching Earth-facing geometry, a thermosphere running warm, and the 10.7 centimeters radio flux holding at 100 for solar flux units, not extreme, not catastrophic in isolation, but positioned within a cycle that has already exceeded its predicted envelope and produced an S for severe radiation storm in January that stood at the top of the GOES proton flux records. The January 18th CME traveled at approximately 1,700 kilometers per second. It was not detected in its final speed until it arrived. Initial estimates had put it closer to 1,400 kilometers per second, a number that proved materially wrong and that compressed the actual warning window relative to the published forecast. Minutes are not hours. In this context, that difference is everything. A CME detected at 1,400 kilometers per second gives a specific arrival window. The same CME at 1,700 kilometers per second arrives hours earlier, while protective measures are still being calculated rather than implemented. Grid operators who rely on NOAA's Space Weather Prediction Center alerts work with advance notice measured in hours, and they use those hours to reduce system load, adjust protective relay settings, and coordinate with regional transmission operators. An event that arrives faster than forecast compresses that window. An event that originates from a far-side region that was not fully characterized before it crossed the limb compresses it further. There is a location on the planet where the combination of grid exposure, geomagnetic latitude, and population density creates a condition of particular consequence, the northeastern North American power grid serving Boston and the surrounding region of approximately 4.8 million people in the greater metropolitan area, and extending across a transmission network that was largely built in the post-war decades, sits at roughly 42 degrees north geographic latitude, which translates to a corrected geomagnetic latitude where geomagnetically induced currents are consistently elevated during G3. And above storm conditions, the residents of this grid service territory go about their lives with a specific assumption built into every daily transaction, that the electricity will be there. That assumption is not technologically guaranteed in the way it might be if every transformer on the network had GIC blocking capability, every relay was set for space weather scenarios, and every spare transformer was pre-positioned within hours of the most vulnerable nodes. Some of that preparation has been done. The Federal Energy Regulatory Commission's Order 779, issued in 2013, directed the North American Electric Reliability Corporation to develop geomagnetic disturbance reliability standards. Utilities in Ontario installed GIC detection devices at strategic transmission locations, but the gap between the standards that exist and the full hardening that an S for class or higher event would require is a gap that power engineers know exists and that grid planners have struggled to close against the competing demands of day-to-day infrastructure budgets. The medieval solar storm, now documented in the tree rings of preserved organic material, provides the deepest historical perspective on what the sun is capable of outside the instrumental record. Research published in May 2026 by scientists at the Okinawa Institute of Science and Technology using an ultra-precise carbon-14 measurement technique refined over more than a decade identified evidence of an extreme solar proton event during the period from approximately 1190 to 1220 AD. The carbon-14 signal was detected in ancient tree rings with a method sensitive enough to identify weaker sub-extreme events that were previously invisible to the science. The event from the medieval period produced red sky or auras documented in historical records across Asia and Europe. It occurred near the peak of a reconstructed solar cycle, a finding that is directly relevant to the current moment because solar cycle 25 is operating at or near its own peak, the solar maximum that the prediction panel placed between November 2024 and March 2026. The researchers noted that some of the prolonged low-latitude or aura from the medieval records seemed to fall near the minimum of the reconstructed solar cycle, a finding that their own lead researcher, Hiroko Miyahara, voiced, described as unexpected and requiring further investigation. This matters. It means that even outside solar maximum, extreme events can occur. The geological and dendrochronological record holds the evidence. What happened between 1190 and 1220 happened without warning systems, without prediction models, without monitoring satellites. It left its mark in the carbon-14 levels of buried trees that were still standing when the astronomer Carrington was alive. The record of it is still preserved in the wood. What is happening on May 20, 2026 is not the Carrington event. The data does not support that characterization, and the temptation to reach for the most alarming parallel available is a temptation that the verified data does not justify. What the data supports is more precise and in some ways more difficult to sit with than simple alarm. It supports the statement that a solar cycle running above its predicted envelope at or near its maximum, with a thermosphere heating index in continued ascent, has produced a far-side active region now rotating toward Earth-facing geometry, whose full magnetic character is not yet resolved, in a period when NOAA's space weather prediction Center has flagged publicly that the forecast is subject to change beginning today. That is not speculation. That is what the official sources say, in the careful language of forecasters who understand the difference between what the instruments show and what the instruments cannot yet see. The question that remains open, the question the viewer carries into the silence after this narration ends, is the one no instrument currently in operation can answer, not whether a significant event can originate from the region now rotating into view. Not whether the grid infrastructure in the path of a major geomagnetic storm carries documented vulnerabilities that have been studied, quantified, and in many cases not yet remediated. Those things are not questions, they are documented. The open question is whether this rotation, this approach, this particular convergence of a strengthening solar cycle, a warming thermosphere, and a far-side active region crossing the limb on May 20, 2026 will produce what the pattern says it could. The instruments will answer that question over the coming days. The forecasters will update the 3-day forecast as the region resolves into near-side geometry and the full magnetic classification becomes possible. The grid operators will read those updates and make their decisions accordingly. What will not change, regardless of this specific event's outcome, is the larger fact that the instruments are now recording. Solar cycle 25 began in December 2019 with a minimum smoothed sunspot number of 1.8. It was predicted to be modest. It was not. It produced an X1 9 flare and an S for severe radiation storm in January 2026, the most intense radiation storm in the GOES records at that level. It produced for X-class flares in 48 hours in February. It maintained a thermosphere heating index that by May had climbed 216.56 times 10 to the 10th watts against a historical minimum of 2.05 and a historical maximum of 49.4, and the approach is not yet complete. The sun has been doing this for 4.6 billion years. Human civilization has been building its critical infrastructure for less than 200 of them, almost all of it during a stretch of solar activity that, against the multi-century record now being reconstructed from tree rings and ice cores and historical documents, qualifies as the quiet period, the instruments that now watch. The far side of the sun are the newest addition to a monitoring system that has existed in its modern form for barely 7 decades. Solar cycle 25 arrived stronger than predicted. The far side region is rotating. The thermosphere is warm, and the record written in wood and ice long before anyone had instruments to read it shows that the sun has done far more than this before and left no record of having given warning.